while we're live.
Okay.
Isn't that classic us?
It is. It
Yeah.
is.
Yeah, no, we should expect this. We should be live now. Yeah, we should totally expect this, right? I mean, I dismantled my entire computer system, so there's got to be some collateral damage. And you're in
A
where?
very boring office. I'm going to try and rotate this so it looks less boring. I'm going to try very carefully to rotate this. So at least there's like a filing cabinet behind me.
And look at that, you got like a little light right on your face.
I do. I do. You can see it in the side of my video, except you've probably cropped it for
I
the
have. I
audience.
have, yeah. Here, let me see if the audience can see it now. Nope, I've cropped it.
There.
There it is.
See? I have a
Just putting
little
it on your
tiny
face.
light.
There you go.
No light. Light.
The magic of Hollywood. I have the same thing. Light, no light.
I think your monitors are dominating at the moment.
No, I have a fill light right here, right here.
Oh, okay.
See the
Yep.
difference? Oh, Bill Sugden is saying there will now be a short silence in remembrance of Google Plus. Yeah, unfortunately, we're
Did
uh,
it go down today?
April 2nd. They're going to just delete everything,
Okay.
everything you've ever done. I should say
Okay.
hi to some people. Hello to Ben Kalo, Bill Sugden, Bor Clankar, Catalin Bontia, Chai Latte Nebula, Dwayne, Dane Coviu, Elad Avron, George Lancaster, Giselle Sabrin, Gordon Dewis, Guido Bierbrock, Harry M, Helge Barkog, John Suffield, Johnny Zed, Larry Beckham, Linda Sadiq, Michael Bonnet, Nancy Graziano, Paranor, Richard Hayes, Rick Schwartz, Susie Murph, Tak Tang, Umu, and Zapfen Zapfen. Hey everybody,
I
welcome.
wonder if Johnny Z goes every time.
Every
I'm
time
Johnny Z because Johnny Z is like a thing.
you're gonna need to have an American co-host to your show if that's what you need. But I
No,
think
I'm fine. I like Z. It makes sense, and it's much easier because like B, Z, D, they all sound the same if you're not careful. So
uh
Z at least is
yeah,
unique.
that's exactly right. No one ever in Canada goes, "Did you just say C or B or G?" All right. So what's going on? But it's not cold there. But you were telling me before that you have a bit of survivor's guilt for being in
I
a
I
warm
do.
place.
So I am currently in an exceedingly boring visitor's office at the Planetary Science Institute down in Tucson, Arizona. Um, the office is boring, but the trip has been the exact opposite. I've been meeting with all sorts of people, hearing all sorts of cool science, plotting and planning all sorts of cool stuff for the future. I get to fly home tomorrow, and it's been in like the 70s, the high 20s if you speak centigrade, the whole.
Nice. Their internet's not so great though, clearly, because you've cut off. Okay. Well, while we wait for Pamela to sort out what's going on with the internet there, she was just talking about how great it is there, and now it's warm, but it's so warm that it's fried the internet. So something for the future. All right, let's do it. Dane Cuveyo. Cuveyo. Dane Cuveyo. I cannot promise that I'm going to get it right, Dane. It's just me, two of me. All right, I'll go back to me here while we wait for Pamela to find some internet. Or we just wrap this up. Let's just turn this into a QA show. So if you got some questions for me, hit me up. Come back, Pamela. All is forgiven, says Ponder. Satellite internet can't come soon enough. So did everybody hear today that Elon Musk has decided that they're going to the moon first, and they are going to be streamlining the development of the BFR, the Starship, and they're going to be doing a Raptor engine that is both can be on the same on the Super Heavy as well as on the Starship. And the plan is whatever they can do to get to the moon as quickly as possible. People wondering what the secret twin is. I'll show you how this works. So So I have two cameras. I wish I could like show you a mirror or something. I have two cameras on my computer. One that is the one that I'm displaying, and then another one that's kind of like a monitor that the people who are in the hangout or in the show would see me. So it kind of looks like, I'll show you what it looks like from my perspective here. Let's see. All right, so you should see how this is going to work.
Hello.
Hey, just sort of showing.
I'm on a different subnet. Hopefully it will work better now.
There you go. So I've got two cameras pointed at me, and so all of the people that I'm in the show with, they see. I guess we're not going to be able to show it now. See, I can do this. There we go. So they see this terrible camera that looks like this, and you see everything is backwards. You can see the text there is backwards. So, because that's my really low quality camera, and then, so that's what, and I'm sure they think I have, this is the quality of the. No, we have a much nicer quality that's being broadcast, which is the camera that you're seeing right now. So there you go. That's how it works. And so whenever you see that sort of like really washed out, overly poor white balanced camera, that is the secondary camera that the people in the show see with me. But I can blow their minds, and I can have them see what the show looks like. So now this is, whoa, that didn't work. What? She sees herself.
I do.
Yeah. And let me see if I can, I think there's a way to be able to show people this. Oh, well, which is sort of cool. So back to what you get to see. There you go. All right. What happened? You were just telling us how wonderful this place is. Clearly, the internet is one thing.
So I accidentally logged on to the guest Wi-Fi instead of the you work there Wi-Fi, and one of them is a better Wi-Fi than the other.
Right.
So it's fixed.
Good. Congratulations. All right. Well, now we've killed enough time. It's time to actually do our episode of Astronomy Cast. Are you ready-ish?
Yes.
Okay.
I am ready to press record. Are you ready to?
I am also. I have just pressed record. I'm not even going to wait if I'm ready.
Press record too.
Okay.
Hold on. I have a monitor. I need to try this again.
Okay. I will stop mine.
I can hear myself on delay, and that's just wrong.
Is that coming from me somehow?
No. It was in Audacity. I accidentally had the monitor turned on.
Okay. All right.
Okay. So I've restarted. Hello, Susie.
Hello, Susie. You can hear me okay. All right. Here we go. Astronomy Cast, episode 516, Polar Vortices. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser, Cain, publisher of Universe Today. With me, as always, is Dr. Pamela, a senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing?
Good. And where are you right now?
I am in the visitor's office at the Planetary Science Institute's headquarters in Tucson, Arizona. It is a very boring room in a very exciting building.
Right. So you are a senior scientist for the Planetary Science Institute, and now you're a senior scientist at the Planetary Science Institute.
Exactly.
Right. And that's the thing that people don't realize, of course, is that in this new virtual world, Pamela's always on the move, normally working from home. But every now and then you get a chance to actually go into the office and hang out and visit with the people there. And well, actually, I'll get into the weather in a second. But what's it like? I mean, how many people how big is the place?
So I haven't actually figured out how many people are located here. It's in the tens. I can tell you that much.
Right.
The Planetary Science Institute in general has over 100 PhDs and all their support staff. And this means that like Susie's going to be working at the Planetary Science Institute. Nancy's going to be working at the Planetary Science Institute. And part of the reason that I'm here is to work on transforming all of your donations, all you wonderful people out there in the audience, into offers of employment to all of our staff. So your Patreon contributions are the reason Susie has a job and can pay tuition for her daughter in college. So if you've thought about supporting us on Patreon and have never really done it, you need to go to Patreon now and help Susie get paid.
Perfect. All right, so it's cold right now. Okay, fine. Here on Vancouver Island, it's actually pretty warm. But for the rest of Canada and big parts of the U.S., it's terrifyingly cold, colder than Mars or the North Pole cold. This is all thanks to the breakup of the polar vortex. What are polar vortices? How do they form? And where else do we find them in the solar system? So, ironically, of course, where you were just days ago was at the heart of the polar vortex. How bad is it back at home? How your husband, when you talk to him, what kind of frozen state is he experiencing?
So I really have survivor guilt this week. Uh, it has been getting to a wind chill of minus 25 Fahrenheit, which is minus tens of degrees centigrade. And it is so cold, our dogs are not allowed outside for more than 5 minutes because their eyeballs and noses and things like that will start to freeze in bad ways. Um, and we're in St. Louis, where normally this time of year, it's right around freezing, plus or minus a few degrees. And to go from right around freezing to an air temperature of, before the wind chill happens, about 0 degrees to plus or minus 5 degrees Fahrenheit to minus 15 degrees plus or minus a few. It sucks.
Yeah, yeah. We normally, here normally we hover like in the 3-4 degrees centigrade. What's that, in the sort of in the mid 30s for the Fahrenheit folks. We can have cold snaps that'll take us down to about minus 10. Like a really bad winter cold snap is minus 10 Celsius, which is in the low teens, I guess, for you, or the aughts. But yeah, this polar vortex is hitting the folks in the U.S. Like, I've heard wind chills in Chicago of minus 55. 40. I've heard minus 55.
Yeah. Okay.
And Winnipeg, which is just a really, really cold place, is experiencing just insanely cold weather. And they are blaming this on the polar vortex, or more specifically, the polar vortex not doing what it's supposed to be doing. It's moved. So what is a polar vortex?
Worlds like our own Earth that have variations in temperature between the equator and the pole will end up with these convective cells. This is super easy to see in images of Jupiter, where you see these bandings of lighter and darker material that are actually counter-rotating around the world. Well, here on Earth, we have a series of jet streams. We have the tropical jet streams and the polar jet streams. And these are demarking the areas where we have our own alternating bands, our own convective cells within the atmosphere. And ideally, you have this great, the pole is super cold, and you have this nice, low density, super cold, massive air that is counter rotating at the top of the world, the bottom of the world. There are jet streams on both sides that are locking those in. Then you have another band of warmer air, another band of even warmer air, and you have these alternating bands with these jet streams, and everything stays put because of thermodynamic differences. The colder the Arctic, the warmer the equator, the happier the planet.
And that's what happens normally. And we should, I'm sure people are going to want, we should definitely sort of go down the rabbit hole for a moment just to talk about it's all gone horribly, horribly wrong right now. But then go back into more normality and sort of deal with it, what it's supposed to be. How has everything gone horribly, horribly wrong right now?
Well, so the reason that you are in a good place in St. Louis, where you and I normally have about the same weather,
Yeah.
Is those Rocky Mountains serve as a buffer for you. You're on the correct side. and death for me, because the jet stream is sort of like, I don't know where to be. The temperature gradient isn't what it should be. And that blob of cold air sitting on top of the world, instead of being a tightly focused cyclone of air, has fragmented into multiple low density, low pressure pockets. And those pockets are wandering free, and they're coming my way instead of your way, because they're just drooping down those Rocky Mountains. The air coming off the Rockies is shaping where they end up going. And this isn't just a North American thing. We also find that the Ural Mountains in the the Ural Mountains in Russia cause a similar effect to occur, where Siberia periodically also gets a polar vortex sitting on top of it. And it's just the jet stream no longer being correctly shaped, because there aren't the thermal gradients to drive where it hangs out as there should be.
And so you get this situation. I mean, I sort of think, and I don't know if this is the exact same situation, but you open the door to one of those big walk-in freezers, right? And warm air from where you are goes into the freezer, and the
Yeah.
cold air spills out. And normally the all of those temperature gradients, all of those spinning bands that are going across the planet that are routing around the landforms on the Earth are acting like this natural barrier. They are the walls of the freezer that are keeping that incredibly cold air properly up in the poles, and down in the poles where it belongs. But in this situation, I mean, you can see these simulations. NASA does these amazing simulations of where the wind patterns are going, and where the warm air is and where the cold air is, and these beautiful, almost artwork like maps showing these arrows of where things are and temperatures and so on. And you can see these jet streams, which normally stay, they push up along, as you said, up along the mountains, and they curl away off into the ocean, on both sides. You know, that's one of the reasons why Iceland is so reasonably warm, is you get this jet stream that passes right above Iceland when it normally should be minus 40. It's freezing, or just a little below. And
And,
so,
and our oceans also hold on to the thermal reserves, which is why you can be so far north. You're roughly 400 and something, not 500, but you're a lot of miles north of Chicago and Milwaukee. And so even though you're more north than Chicago and Milwaukee, you never have that
yeah.
blistering cold weather those two cities get.
Yeah, and thanks to being beside the ocean. And so normally, just on a normal year, all of these things are in lockstep, and occasionally, I mean, this isn't. I mean, I can remember it was about 3 or 4 years ago. Susie will tell us exactly when they were getting like minus 10 degrees in Atlanta, where she lives, and it was just mayhem, and same
Yeah.
situation. And that's normally a very warm place, and so you got this another situation where the polar vortex had fragmented and moved around. So let's address the elephant in the room.
Yeah.
People have said, where's our global warming? Everything is so incredibly cold. This is because of global warming, right? This is a
Yeah.
result of climate change.
And this is where we have
Maybe,
to remember.
probably.
No, it is. It flat out is. So the science of this is that as the average temperature of the planet increases, we're seeing the ices that normally cover the Arctic Sea are melting. And instead of reflecting light back up away from our world in wavelengths of light that are happy to radiate away, instead, the heat is getting sucked into the oceans that are no longer capped with that wonderfully reflective ice. The oceans are warming up. They're irradiating in the infrared, which does not escape through our atmosphere. And so instead of having this wonderful cold area that is reflecting all the warming light away, the ocean is absorbing the heat. The same is happening with the land. And we're also seeing the permafrost, the tundra, these areas of frozen Siberia, Alaska, these areas are melting. And so now the ice reserves, the temperature reserves of coldness in the soil is also going away. So now we have heat being trapped in the land, we have heat being trapped in the ocean. And we generally see the polar vortex lessen in summer. We always have seen, since we had satellites in the air, that some of the Arctic Sea broke up in the summer. And during the same period, we'd see the jet stream become more erratic in its behavior, dipping down further towards the south. And that jet stream ducking southward is a sign of a polar vortex that is no longer tightly confined, that has weakened and fragmented. And one way to think of this is if you've seen hurricane images, as that hurricane deteriorates into a tropical storm, it fragments into multiple pieces. And you can still see hints of the structure in that tropical storm. But it's only when it's a fully formed cyclone that you have that beautiful spiral structure. The polar vortex is actually a cyclone of air movement. It's just not a storm movement, but it has that same physical structure. And when the needed conditions aren't there, it fragments into multiple pieces. And just like as that hurricane turns into a tropical storm, you'll get bands of rain going in all directions. When the polar vortex fragments, you get blobs of cold air going in various directions. And it all comes down to what the thermal gradient is. And right now in the winter, we're not seeing that completely frozen terrain. We're not seeing that completely frozen Arctic Sea. And this means we don't have that amazingly cold thermal gradient, that amazingly strong vortex of cold air. And instead, we have this fragmenting system.
Right. And so, I mean, for the people who are like, boy, I sure wish we could have some global warming right now, don't worry. In the summertime, everything will be on fire and there'll be horrendous droughts. So,
Yeah.
so it's these extremes now where you get a winter that doesn't behave like a winter is supposed to, and you get a summer that isn't supposed to be, that doesn't behave like a summer is supposed to, and the two go hand in hand. So let's, I mean, we don't want to, we freaked out about global warming and climate change in other episodes, so we'll save that for a future episode. So let's talk more about some of the science of these polar vortices, because we find these across the solar system. What are some other places where we see these polar vortices?
So Venus is one of the more intriguing ones because it doesn't have just a single polar vortex per pole like we have here on Earth. Rather, this slowly rotating world, it still has the effects that lead to a polar vortex, but it actually has a double vertex at its pole. Now, this is where it's important to remember that cyclones are caused by you have two air masses at two different temperatures, one cold, one hot. And that freezer analogy you gave of you open the door and you feel the cold air get displaced out towards you as the hot air rushes in. Now, in that case, you have this linear exchange of temperatures. With a rotating planet, the Coriolis force is like, no, I'm going to make you rotate. And that Coriolis force is what drives hurricanes, what drives the polar vortex to move the way it moves, and to give us these spiraling storm patterns. If you look at the current images coming down off of satellites like the Terra satellite, showing amazing storms coming off of the Great Lakes region. Now, with Venus, you
Yeah.
still have the Coriolis force because it is still rotating, but its day is longer than its year. And this super slow rotation means that the Coriolis force is like, I think I'll rotate. I think I will do something. And it doesn't lead to this tightly focused storm such as we see here on Earth on top of both of our poles. They instead end up with the super cool double vertex.
And it's, I mean, there isn't anything right now, but we got some pretty great photos that came from the Japanese spacecraft that's at Venus right now, I can't even say it. Akatsuki.
I'm going to let you do that.
Yeah, and I'm sure someone is gonna fix that. But you've got this. you can't see it in the visible light. Like here, you can see the cloud movements and you can see, with visible light. But with Venus, you need to use infrared to be able to
Yeah.
see, peer through these really thick clouds, and you get these amazing, as you said, double polar vortices that sort of go around each other with all these other high level clouds that are
Yeah.
swirling around it. And so for the longest time, the dog is freaking out upstairs. I apologize for anyone who can hear this. You get, we thought that Venus was just dull and bland, that everywhere on the entire planet was the same temperature. And it is, but there are still in the upper cloud tops these really great movements. And it's still because Venus is turning, it has a tremendous atmosphere, and you get these motions. But the coolest ones are on, I think, Saturn.
Yes. So Saturns we can't fully explain because they're actually hexagonal in shape, where there are standing waves, as best we can tell, built up that cause essentially flat sides going around the eye of the vortex. And here on Earth, we can't generally just look at a pole and go, yes, there's a polar vortex, because it's clear air that happens to be moving. It's like you can't see the wind unless there's clouds in it. And the cold air on Earth over the poles is super dry. It's only when that cold air sweeps across, for instance, the Great Lakes and picks up moisture off the Great Lakes and then buries Ohio, that lake effect snow of the dry air going over a warm body of water, picking up the moisture, dumping the moisture. Then we can see it. So these terror images we're seeing allow us to see the cold air picking up the water, clouds forming. Well, on worlds like Venus, where you have clouds everywhere, on worlds like Saturn and Jupiter, where you have clouds everywhere, the exact structure of these polar vortices is obvious in the images without having to model out the winds. Venus, you have to look in a different wavelength, but with Saturn, it's just there in visible light, actually allowing you to look down the eye of this polar cyclone and see deeper into the layers of this world's atmosphere.
I'm putting, for the people who are watching the live show, I'm just putting up a picture of it beside you so that they can see what this looks like. And it is just the weirdest. It's the weirdest thing because it is absolutely this hexagonal shape with swirling clouds and swirling clouds and tiny storms, and then in the middle it just goes down to this
Hexagon.
the hexagon, and and you say it's a mystery, right? Like we don't know
There's
completely.
lots of conflicting theories.
Yeah,
The word standing wave is used pretty consistently.
right.
So, whatever the physics is, it involves probably something that generates standing waves.
Right, and people have been able to sort of simulate this when you have like, you've probably seen this like a science center where you take this. There's like a big disc with some kind of material inside of it, and you spin it, and you get these interesting shapes in that from these fluids turning of different densities and so on. And so there is something going on, as you said, a standing wave that has something to do with densities and different kinds of fluids. And we see something kind of analogous on Jupiter as well. I think it has its own version of
Yes,
of
and we
its own.
even actually see this on Mars sometimes. So Hubble has been able to image colossal polar clouds over the poles on Mars that shape out vortices. Here again, we have to wait for there to be clouds in the right place, but Mars, with its atmosphere, does sometimes put on a show.
I've got just a research article here talking about the stability of Mars' annular polar vortex. So, same kind of thing. Now, of course, they've got 1% the atmospheric density that we have here on Earth. So there's only so far that you're going to get. So, I mean, would you expect to find this on Titan? Like, literally any place that is rotating with an atmosphere, you would expect to find this kind of a structure.
It all comes down to how much of a temperature gradient do you get? And so with Titan, what I don't know is how the interplay of reflected light off Saturn, of its extreme distance from the sun, its small size, its tilt. I don't know how much that will drive vortices. So if it has them, they're probably they. I'm not going to say probably. I don't know. They could be wussy. They could be strong. It all depends on how all these different factors interplay. And what's interesting is most of the worlds we've talked about, you have cold polar vortices because the pole isn't exactly pointed towards the sun in general. And it's at such a great angle that the light that does hit it is coming in at a severe angle. And so when you look at these convective cells, the numbers of the convective cells are such that the pole is cold. But Saturn likes to fool us. And Saturn, with its hexagon, is the only warm polar vortex that a world has. So the question becomes, as we look at worlds and we go from planet to moon, are we going to find cold or warm? And these are things that, as people pour through all of the Titan data now that Cassini's over, what are they going to piece together and find?
And one of my sadnesses is that we don't have any spacecraft at Uranus and Neptune. And I would assume that both of these will be absolutely fascinating for future observations, because with Uranus, the whole planet has rolled over on its side, and it spends half the year with one pole facing the sun and then half of its year with the other pole facing the sun. What must that do, where the rotation is kind of perpendicular to the way it's being illuminated from the sun? That must create some really bizarre atmospheric effects.
Coriolis effect.
Yeah, and I mean, we see some of the storms on Uranus, but we really do need an orbiter to hang out there and spend a long time being able to orbit it. Of course, even just by following in on the plane of the ecliptic, it should come naturally into a nice polar orbit that would allow it to go around and see the North Pole and the South Pole and the North Pole and the South Pole. And then you get Neptune, which is farther out, colder, receives less heat from the sun. What kinds of atmospheric stuff is happening there? And all we see is, we've got a couple of images that were taken by the Voyager spacecraft, and the best that Earth-based telescopes can do. Those would be ideal places to go and understand.
And with Uranus, we just never get to see that far side that is not pointed at the sun. Just the orbits don't let us get there from here. Unfortunately, right now, the energy, the delta V required to go from on your way out to Uranus and Neptune to then going towards it to now being in orbit around it, that's a huge delta V. And no one's been willing to build the spacecraft that has the capacity to do the delta V for a get there quickly. And no one has the patience to build one for the get there slowly and require less energy to get in orbit.
Yeah, and there are. I mean, I've reported on this several times. There's a couple of proposals in the works. Let's talk a bit about extrasolar planets, because what we're really finding with our discoveries, thanks to Kepler and now TESS and all of these other spacecraft, is just the extremes that are out there. Would we expect to see extreme versions of polar vortices for some of these worlds? I'm thinking about things like hot Jupiters and things that are tidally locked to their stars and things like that. Like, what kinds of unusual situations could we expect to see?
So I have a light, so I can really do this demo well. So if you have a rotational axis that is pointed towards your star, you're probably going to end up with something weird that doesn't involve strong polar vortices. If, however, you are perpendicular to your light, rotating around rapidly, so more rapidly than we generally see. So Jupiter has roughly a 9-hour, Saturn is again several hours in rotation. These rapidly rotating worlds see very strong polar vortices. So imagine having an Earth-like world that's rotating much faster. It's going to have much stronger polar vortices. It's going to have much stronger Coriolis forces, and that starts to get much more exciting, perhaps more exciting than you might wish to live on.
Yeah.
but I'd still like to see that.
And then you also imagine those worlds, those like, for example, water worlds where they have no continents, and that
Yeah.
the planetary bands can go all the way around the planet. But you would almost expect then the polar vortices to be very well behaved, because you're not going to
Yes.
get these changes. You're not going to get a lot of movement north or south of as the jet streams attempt to move
And this is
around, right?
exactly what we see on Jupiter.
Yeah, yeah. Perfect bands in opposite directions, side by
Yeah.
side, chopping up the planet into little slices.
It's our silly mountains and landscape that makes it so hard to predict the weather
So we could have a nice, dependable winter weather system if we flattened all the mountains,
and made sure that the temperature gradients were constant.
filled in the oceans, flattened out the mountains, and just made everything perfectly the same.
I think this is something that we just need to get on.
Yeah. All right. Well, we'll put that in our list of geoengineering suggestions.
Okay.
All right. Thanks, Pamela. Enjoy the warmth there,
I am. I really am.
and we'll talk to you next week.
Bye-bye.
All right.
And yes, Susie, I'm going to upload this before I go anywhere. I know, I know, I know. I have a terrible habit when we're not in our normal places of not waiting for my computer to fully upload
Yep.
and then wandering off.
Right, and it's stuck on that computer,
Yeah.
and you might be in a different continent from that computer.
Yeah. Well, I've never been quite that bad, but I might be nowhere near the internets.
I
So
have made that
this
mistake. I have made the do the show, forget to upload, go on a trip, and then I have to
this
talk
is
someone.
this is 516.
Yeah.
Okay.
Sorry, while we hang tough, while we record, so while we save.
And I do need to keep the questions short.
Okay, no problem. Actually, that
Sorry,
works for me too,
everyone.
because I've got to go and record another podcast. I'm
Okay.
going to be on the Oceanside Photo and Telescope Space Junk podcast in about
Excellent.
20 minutes. So, and we're going to be
Excellent.
talking about pseudoscience and conspiracy theories. So that's going to be fun. Favorite
Awesome.
topic? Not favorite topic. All right. All right, I'm ready to upload, but I won't yet, and we will talk. Hit us with your questions. Let's
Short
see.
ones.
Okay, so Chai Latte Nebula asks, could a neutron star have vortices?
No. No.
Wait. Neutron stars, can't they have some kind of atmosphere that is like a different matter on top, and the things are spinning so ridiculously fast? Neutron star crust.
It's like atoms thick.
Yeah.
So I don't think it's going to be able to form a full-fledged vortice.
What
And
about? Yeah.
and
Okay.
the magnetic field isn't aligned with the rotational axis, which will create chaos.
Right. I mean, part of it is like, what's your definition of an atmosphere, and what's your definition of, and the dominant force at a neutron star is the magnetism. That's
Yeah.
whirling things up. And Thompson asks, not related to vortices, what is the telescope behind me? What kind of telescope is that? Is a 70 millimeter stellar view apochromatic refractor telescope.
Yeah.
So it is like a, like when you get a telescope, like you're a pirate and you look through the telescope, and you got a lens.
But it's apochromatic, so you don't end up with rainbows at the edges of
Right.
stars, which is
Yeah.
awesome. It's
Yeah.
my favorite kind of telescope.
Me too. Me too. I really love the view through a refractor, and the problem is I have such terrible view to the skies here. So
Yeah.
literally from September through spring, I have only a couple of clear nights every month, and then during the
Sadness.
summertime, I have a ton of neighbors with with bright lights all around, and we have a lot of trees around us as well. So I just don't have a great view. Like, I can't see much with it. So I more rely on all of the cool virtual telescopes that our good friends at
Yeah.
OPT let me use. So I take that out in the summertime when the weather is nice and there's something interesting happening in the sky.
Cool.
Yamagashi-san asks, if photons have no mass, why do they succumb to the immense gravity of a black hole?
Because they do have energy, and energy and mass are interchangeable. So it's the energy that's getting pulled on by the gravity.
And the point is that gravity distorts space-time. It makes
Yeah.
photons, which are traveling in a straight line, think they're still going on a straight line as they follow the distorted space-time. And so,
Yeah.
for example, satellites that are orbiting around the Earth, they think they're going in a straight line, but the Earth's gravity is twisting space-time so that what you think is a straight line is actually a curved line. And
Yeah,
so,
so for instance, they're on the inside of a bowl, in this case simulated by an orange peel, and they're moving on a straight line along this surface, but while it's a straight line along this surface, it's a curve in the three-dimensional space.
Ben Kalo asks, ULA just announced the contract to send Lucy to Trojan moons. What do you know about that?
Nothing.
I know. Okay, so the Lucy, and I think I'm going to do a video on this now that this has been announced. So the Trojan moons are the moons or are asteroids that are trapped in the Lagrange 4 and 5 points around Jupiter. And what's helpful about doing, and so the Lucy mission, what it's going to do is it's going to go out to Jupiter. It's going to go to one set of the Trojan asteroids, and then it's going to move across the Jovian system to the other set of Trojan asteroids. And one of the things that's really great about the Trojan area is it is a trap for space rocks. It's a place you can go and just see all kinds of different samples that Jupiter's gravity happened to capture and then move to the other side. So it's sort of like if you wanted a place where a whole bunch of really great asteroids have all been collected together so that you could just examine them in one place, that's the place that you go. And so Lucy's
And
going to
of
go
all different kinds.
of all different kinds. And so Lucy's going to go to one. It's going to sort of orbit around this Lagrange point and see all of the different kinds of asteroids that are there and observe as many as it can. And then it's going to move over to the other side and do the same thing. And so getting out to Jupiter, having the propulsion to be able to go to both of the Trojan points is going to require a lot of juice. And as we saw with the Parker Solar Probe, ULA can build some rockets that can make things go very quickly. And
Yes.
that sounds great. And I'm sure the folks at ULA are very excited. I mean, they've been supplying the launches for most of the big. They provided the launch for InSight.
Yeah.
They'll do this Lucy mission. Most of the missions, most of NASA's missions. We're starting to see some stuff from SpaceX, and I'm sure when the Falcon Heavy really gets cranked up, we'll see more of these bigger missions using that.
Yeah. I do need to get going.
Okay, well then let's wrap things up. Before we do, and just call back to earlier, as Google Plus is leaving us, don't forget to join our good friends at the Weekly Space Hangout crew. That is the community that really supports everything we do, organizes a lot of the behind-the-scenes stuff, and it's a great community. So go to wshcrew.space and join that amazing community. All right, we're going to wrap things up. Thanks, everyone, for watching. I'm going to go do this podcast. If you haven't already, subscribe to the Oceanside Photo Telescope Space Junk podcast, and you hear me rail about conspiracy theories in about 15 minutes. Well, I don't think it's going to be live in any way. Pamela, have a safe trip back. Don't forget to upload. And
Already done.
Okay, great. And we'll see you all next week. Bye, everyone.
Bye.